Hello, dear student. Myself, Dr. Surekha Jaiswal, Head Department of Physics, Moreshwar College, Bhokardan, District Jalna. Today we will see Mechanics Properties of Matter and Sound, course code number 101. Now we see here gravitational field due to a solid sphere. Gravitational field at a point outside the solid sphere. Now also here we see gravitational field at a point inside the solid sphere and gravitational field at a point on the surface of solid sphere. Also we have determined gravitational potential due to a spherical shell. Having gravitational potential at a point outside the spherical shell and also gravitational potential at a point inside the spherical shell and gravitational potential at a point on the surface of spherical shell. Also we see here gravitational field due to spherical shell. Having gravitational field at a point outside the spherical shell and gravitational field at a point inside the spherical shell and gravitational field at a point on the surface of spherical shell. Now see gravitational field due to a solid sphere. Now gravitational field at a point outside the solid sphere. Now we know that the potential at a point outside a solid sphere having distance r from its center is given by V equal to Gm upon r. Now here since gravitational field due to a solid sphere at a point is equal to the potential gradient and the gravitational field due to solid sphere at a point distance r from its center, that is E equal to minus dV upon dr. So putting the value of V, we get E equal to minus d dr into minus Gm upon r. That is the value of V. So after differentiation we get E equal to minus Gm upon r square. Now here G is a constant, so taking out and differentiation of this m upon r is here. M is also constant, so differentiation of d dr of 1 upon r is equal to minus r square. So E equal to minus Gm upon r square. Now gravitational field at a point inside the solid sphere. Now we know that potential at point P inside solid sphere is given by minus m into G into 3r square minus r square upon 2r cube. So since the gravitational field at a point is given by the potential gradient E equal to minus dV upon dr. So putting the value of V here, E equal to minus d dr of V having the value that is mg into 3r square minus r square upon 2r cube. So here also therefore E equal to, after differentiation of this bracket, E equal to minus mg square into r upon 2r cube. So here from this relation m is constant, g is also constant here and capital R is also constant. So E is directly proportional to r, small r. So that is the intensity of the field is directly proportional to the distance from the center of the sphere. Therefore at the center of the sphere r being 0, so intensity of the gravitational field is 0. Now we have determined also the gravitational field at a point on the surface of solid sphere. So gravitational potential at a point the surface of the solid sphere is given by E equal to minus m into g upon r square. So now here we also derive the formula for gravitational potential due to a spherical shell. Now first point is here, gravitational potential at a point outside the spherical shell. Now here suppose this is a spherical shell, see in figure. This is spherical shell and this is diameter of the spherical shell. Diameter is here shown in figure, that is B to A, that is the diameter of spherical shell. And let us imagine a ring inside the sphere shell, that is C, E, F and D. C, E, F, D. This is a ring. Imagine this ring inside the spherical shell. And to determine the gravitational potential at this point due to a spherical shell, and we know that spherical shell is a two-dimensional body. Now we have imagined this ring is inside the spherical shell, and first we have determined the potential of this ring C, E, F, D, and then calculate the potential of spherical shell. So let us consider a point P, that is here as shown in figure, which is distant from R from the center O of spherical shell, having the distance small r, of radius, spherical shell of radius, that is a capital R, and surface density rho. Join OP. Now join this point E and P from this figure and cut out a slice CEFD, that is a ring CEFD, in the form of a ring by two planes close to each other and perpendicular to the radius OA. See, meeting the shell in C and D and E and F respectively. Now let angle EOP equal to theta. See in figure, E, O and P having the angle that is a shown, that is theta. See here, angle EOP equal to theta, and small angle COE equal to d theta as shown in figure. See, that is a small angle having COE, that is a d theta. Now radius EK equal to OE sin theta from figure, therefore equal to R sin theta, that is a radius EK. See, this radius having the value EK equal to R sin theta from figure, and its circumference equal to 2 pi R sin theta. Therefore its width CE having the width, that is a R into d theta, and therefore area of the ring or slice, that is equal to circumference into width. So circumference equal to 2 pi R sin theta and width is equal to R into d theta. So area of ring of this slice is 2 pi R sin theta into R d theta. So is equal to 2 pi R square sin theta d theta, and mass equal to 2 pi R sin theta into R d theta into rho. So mass equal to 2 pi R square sin theta d theta into rho. And if EP equal to x, then what? The potential at P due to this small size is given by dV equal to minus mass of slice upon x into g. So dV equal to minus 2 pi R square sin theta d theta into rho upon x into g. Now in triangle OEP we get EP square equal to OE square plus OP square minus 2 OE into OP cos of theta. So putting the value EP square equal to x square equal to OE square equal to r square and OP square equal to r square minus 2r, OE is also r, OP equal to also r into cos of theta. Now OE equal to radius of shell, that is OE equal to r, and differentiating the above equation we get, now differentiation of this equation, that is 2x dx, x square having differentiate, that is a 2x dx, r square differentiation is 0, small r square also having the differentiation 0, plus 2r into r sin theta d theta equal to 2r r sin theta d theta, r and r being constant. So x equal to 2r into r sin theta d theta upon 2 dx, and therefore x equal to r into r sin theta d theta upon dx. So putting this value of x in equation 1, we get dv equal to minus 2 pi r square sin theta d theta into rho upon r into r sin theta d theta into g into dx, and therefore dv equal to minus 2 pi r into rho upon r into g into dx. So after integrating this value between the limits x equal to ap, that is r minus r, and x equal to bp plus r, we get v equal to integration of minus 2 pi r rho upon r into g dx, integration varying from r minus r to r plus r. So v equal to minus 2 pi r into rho upon r into g, that is a constant. So they are taken out from this integration outside into integral of dx, r integral varying from r minus r to r plus r. So v equal to minus 2 pi r into rho upon r into g, x limit of this here r minus r to r plus r. So after taking limits, v equal to minus 2 pi r rho upon r into g, r plus r minus r plus r. So we get v equal to minus 2 pi r into rho upon r into g into 2r, and so v equal to minus 4 pi r square rho upon r into g, and here 4 pi r square is due to surface area of the whole shell, and therefore 4 pi r square rho is equal to its mass. So v equal to minus m upon r into g, and the mass of the whole shell thus behave as though it were concentrated at its center. So now we determine the gravitational potential at a point inside the spherical shell. Now here also consider the point P to lie inside the spherical shell. See here, this point P is inside that spherical shell as shown in figure. Now potential at point P, see here that point P, due to the slice or ring CEFD, this is slice or ring of the spherical shell having potential, that is dV equal to minus 2 pi r rho upon r into g into dx, taking the limit of this x from r minus r and r plus r, so that we get v equal to integration of minus 2 pi r into rho upon r into g into dx, integration varying from r minus r to r plus r. So v equal to minus 2 pi r into rho upon r into g, integration of dx, r varying from r minus r to r plus r, equal to, after integration we get minus 2 pi r into rho upon r into g, x taking the limit here, we get minus 2 pi r into rho upon r into g. We get here, after taking limit, r plus r minus r plus r. So we get, after simplification, v equal to minus 4 pi r rho into g, and after multiplying and dividing by r, we get v equal to minus 4 pi r square rho upon r into g. So 4 pi r square into rho equal to mass of the shell. So we get v equal to minus m upon r into g, that is potential. Now gravitational potential at a point on the surface of spherical shell. If we consider the point P lies on the surface of the shell, then what? We obtain the potential by integrating the expression for dV between the limits x equal to 0, because the point lies on the surface of spherical shell. So distance x equal to 0 and x equal to 2r, and so that in case dV equal to minus 2 pi r into rho upon r into g dx. So after taking here integration, we get v equal to integral from this varying from 0 to 2r minus 2 pi r into rho upon r into g into dx. So v equal to minus 2 pi r into rho upon r into g, that is a constant quantity. So we can taking outside from this integration, and we get here integral of dx, integral varying from 0 to 2r. So v equal to minus 2 pi r into rho into g upon r. Integration of dx is here, that is x. So after taking limits, we get v equal to minus 2 pi r into rho upon r into g into 2r. Therefore v equal to minus 4 pi r square rho into g upon r, and therefore v equal to minus m upon r into g, and the mass of the whole shell thus behave as those if we were concentrated at its center. Now gravitational field due to a spherical shell. Now gravitational field E equal to here minus dV upon dx. Now we know that v equal to minus m upon r into g. So putting this value in equation, here E equal to minus dV upon dr, we get E equal to minus d dr of minus m upon r into g. Now here after taking derivative, E equal to m upon r square into g. The negative sign indicates that the force is one of attraction, the same as though the whole mass of shell were concentrated at its center. Now gravitational field at a point inside the spherical shell. Now the field at a point is given by the potential gradient at that point, since v is constant for all points inside the shell. So therefore dV by ds equal to 0, and that is the field in the interior of the shell is 0. In other words, there is no gravitational field inside the spherical shell. Now next point is here gravitational field at a point on the surface of spherical shell. Now the gravitational potential at a point on the surface of spherical shell is given by v equal to minus m upon r into g. So here the intensity of gravitational field at a point is given by here E equal to minus dV upon dr. So putting this value of v here, we get E equal to minus d dr of minus m upon r into g. So after simplification, E equal to minus m upon r into g. Thank you.